Not many things in life or on the MCAT are ideal, but we do have a fun law called the ideal gas law, which we can use to represent gas behavior on the MCAT and in life. Today we'll be discussing the ideal gas law and its many derivatives, including Boyle's law, Charles' law, Gay-Lussac's law, and a few important parameters and rules that you need to know in order to do ideal gas law equations on test day. Let's start with a practice question. Go ahead, pause this video, try this question on your own first, and then we'll walk through it together. Okay, so in order to do this question, we're going to need the ideal gas law. We're asked for an estimated volume of a specific gas, X, could be any gas, but they gave us the molar mass, some grams, some temperature, pressure, and a fun unit, R. So let's go ahead and back up a second and talk through what our ideal gas law is and how we can use it to calculate this problem. So our ideal gas law is a general chemistry equation, although there's a lot of overlap here with Gen Chem and physics. And that law is pressure times volume equals moles times the gas constant times T. We're going to go through each of these variables individually, and I'm going to show you how we can actually break these equations down into our sub-laws, Boyle's, Charles, and Gay-Lussac's. Let's start over here with pressure. So pressure, as we talked about a little bit in a hydrostatics and buoyancy video, is the force per unit area that a fluid acts on its container. Our SI units there are usually newtons over meters squared, force and area, but that's often for liquids, right? Not gases. Gases truly expand to fill their full container. Liquids conform to their container, but don't fully fill it up. So that's a difference between a liquid and a gas. Both fluids do conform to fit their container and they both flow. So we'll use newtons over meters squared for a lot of liquids, but for gases, of which this is the ideal gas law, we're going to use a whole bunch of different units. A lot of fun for us, right? So our units are as follows. Atmospheres. This is going to be our typical one, most commonly used on the MCAT. We then have kilopascals. All right, kilopascals, named after Pascal, the researcher. This can also be pascals, right? Kilo is just 10 to the 3, so pascals. We can also have torr measurements, or millimeters of mercury, often used alongside in like thermometers. So we have a whole bunch, and then very rarely on the MCAT, but if you're a scuba diver, you may know this is bar. Bar is also a measurement of pressure. So on the MCAT, we're really gonna only ever see atmospheres and kilopascals for our PV equals nRT. Once in a while, you'll see millimeters of mercury as well, but we'll very rarely see torr or bar. Now, I've listed all these out because I also want to put in the standard pressure. So there's this thing called STP, and I'll write it off to the side here. STP is standard temperature and pressure, and it is essential when you are doing MCAT questions to look out for, oh, is this at STP or is this not at STP? Because that's going to change what we do mathematically with questions like the one before. So STP, the standard pressure of STP in each of these units is 1 atmosphere. That's atmospheric pressure at sea level. 101.3 kilopascals, or around 101,000 pascals. 760 torr, 760 millimeters of mercury, and 1 bar. So this is the pressures you're looking for in order to do our calculations at STP. If they tell you, hey, this experiment was done at STP, this is what they mean by pressure. They will not necessarily give you the pressures. They'll expect you to know what they mean. All right, so that's pressure. It's got the most units. All right, so we've done the hardest one first. Now let's go to volume. All right, volume is our 3-dimensional space that our fluid takes up, right? So our length and our width and our height. Now that's often referred to as a unit of meters cubed, right, or centimeters cubed when we're talking liquids, length times width times depth. But on gases, they're really filling the whole container. And so an easier unit to use, and this is more of our Gen Chem unit here, is going to be liters, right? You'll sometimes see milliliters, which is just 10 to the negative 3 liters. So just note, liters is our only unit that we're going to use for our gas law. If they give it to us in centimeters cubed or meters cubed, they'll often give us a conversion to get back into liters. I'm going to show you why we need liters in a second, but I want you to know we're working with liters or milliliters here in our ideal gas law. Next up is moles. Moles in moles, right? The unit is what it is. Sometimes, like in our practice question, we're going to need to convert grams to moles. So be aware that you may need the molar mass, right? If they give you grams and not moles. But this is often a constant or something we're trying to calculate. Oftentimes we have a container and we don't know how much gas is in it. And so we'll use moles. Our next guy we're going to skip the constant just for a second, and we're going to go to our last variable here, which is temperature. So temperature is going to be always in our ideal gas law, we're going to need to use Kelvin, all right? K for Kelvin. However, sometimes you can get questions that give you degrees Celsius. So remember, degrees Celsius plus 273 is going to equal Kelvin. So you may need to do that conversion. They may not give it to you, but you have to use Kelvin in our ideal gas law, just like we have to use liters. Now, this is included in our standard temperature and pressure. So our standard temperature and pressure, this is really important, is going to be 273 Kelvin or 0 degrees Celsius. All right, that is STP, 0 degrees Celsius or 273 Kelvin. 25 degrees Celsius or 298 Kelvin. These guys are standard conditions, like laboratory conditions. We'll still have the same pressure, it's just the temperature that's different between standard conditions and STP. I will tell you for our ideal gas law and a lot of these shortcuts that we're gonna use, you gotta have the STP. You gotta have the 0 degrees Celsius or else we're gonna have to do the math all the way out. All right, and then now let's talk about our constant here. I'm gonna go ahead and put this in a slightly different color, because it is a constant, all right? That's our gas constant. These often are given on the MCAT. I have really seen most of the time they'll give you R because there are 2 different R's. But just in case, you'll often use this enough in practice that you'll memorize it on test day. The ideal gas constant is 0.0821 liters times atmospheres over moles times Kelvin. You see now why we need liters in Kelvin and atmosphere and moles? Because in order to use this particular R, we've got to have liters, we've got to have atmospheres, we've got to have Kelvin, and we've got to have moles. The units have to match, all right? So if you don't have this, if you have degrees Celsius, right, or you have milliliters, you're going to need to convert your units before using this R. Now there's another lesser used form of the gas constant. This one's one I don't necessarily have memorized. If they want me to use it, they'll give it to me, but I just want to show you in case you get stressed out. Wait, what? Why 0.0821? So there's a gas constant 8.314 joules per mole Kelvin. Joules, right? Now if we have energy, kinetic energy of a gas, this one becomes a lot more useful, right? We're able to do it. And you can see here, there's a 10 to the 3 difference in our 0.08 to our 8, right? So what's going on here? If you could just memorize this, but if you're curious, well, let's think about what a joule is. A joule, right, is a Newton meter, but we don't have that. We have pressure and volume, right? But think about pressure and volume in our SI units. We're gonna come up here. In our SI units, newtons over meters squared times meters cubed. Do that math out. We're getting rid of meters squared and leaving 1 meter. That's a Newton meter. So just so you know, pressure times volume is a joule, right? And specifically the conversion they're using in this particular unit conversion is that a joule is equal to 1 Pascal times meters cubed. And 1 meter cubed is equal to 1,000 liters, right? And so see how it's Pascal. We normally do kilopascal, and then we have a power of 100. So you can actually derive it all the way out to prove that these are essentially the same values. But right now, I just want you to know that this is another form and that pressure times volume equals joules. What is joules? Work or energy, which is why, as a spoiler alert, if you have a pressure volume curve, like in the pressure volume curve of the heart, the area under the curve is work. The work done by the heart, joules. But it's because of the units. Units always have to work themselves out. It's my favorite tip on the MCAT. So just so you know, This is going to be the one you use 90% of the time, the liters times atmospheres over mole Kelvin, but we can also have our gas constant in terms of joules. They'll often give that to you if we have like kinetic energy of a gas provided to us or something like that. All right, so now we've got all of our pieces. We got our PV equals nRT. Let's talk about how we break this equation down. So I'm going to restart this, and then we're going to talk about all the different derivatives, and then I promise we'll get back to that practice question and try it out. Okay, so now I want you to imagine that we have a set amount of gas. So we have a constant amount of moles of gas. It's in a sealed container, right? This is just all full of gas molecules. And so our R is also going to be constant. What if we made this container isothermal? If it's isothermal, that means that we're not changing temperature, right? We have a constant temperature. So we have now made this entire side of the equation just a constant. So you can derive it as just a K, constant. So we have PV equals K. Well, now we just have a relationship between pressure and volume. So you tell me, if I'm increasing the pressure, what's happening to volume here? It's decreasing. Excellent. So this is Boyle's law. We'll go ahead and write it in blue. And Boyle's law basically states that when we are holding temperature constant and we have a set number of moles in a sealed container, if we increase the pressure in that container, the volume that the gas takes up will decrease. Now, what is the relationship between these variables? This is where things get a little mathematically different. I want you to arrange it as if we're going to graph it on a graph. So here's my little graph. So what we need is we need our two variables on opposite sides, right? Like y and x. So this is y and x. So what we're going to do is we're going to leave pressure, and then we're going to divide both sides by volume, right? To get the volume on the other side. So graphically, this is y equals 1 over x. That is a non-linear relationship. I'm going to do my best to draw it here. It looks like this, all right? As x increases, as we increase, y will decrease. But it's never going to cross 0. It's not a linear relationship. It's a reciprocal relationship. So it's an inverse but reciprocal relationship where and you can do this mathematically. You can plot these, we could do 1 over 10, 1 over 100, 1 over 1,000 to really prove to yourself, oh, wow, this is not a linear relationship because of our y equals 1 over x. So this is graphically what Boyle's law looks like, and this is true for any two variables on a single side of an equation. So if you have any variables, if you have x and y equals k constant on the same side, in order to graph it, it's going to have to end up being like this. And that means that it's going to be this type of graph. All right, so this is true for any two variables on the same side. They are inverse, but they're not linear. Okay? All right, and that was Boyle's law. Before we hit Charles and Gay-Lussac's laws and draw them out and also talk about the molar volume of gas, my name is Amanda Brem, and I've been coaching pre-medical students on their MCAT journeys since 2019. Please remember to subscribe to this channel for more videos like this on MCAT content, test-taking strategies, and mental fitness tips to help you perform your best on test day. And if you'd like to join me for over 40 hours of live online instruction where we go deeper into content, do a lot more testing and passage strategy, and have a community of students who are working alongside you to their MCAT goals, go ahead and check out the link below to my next available live online cohort. All right, let's dive back in talking Charles' law. Okay, so we're back to our ideal gas law, but what if this time, instead of holding our temperature constant, we'll still have the same number of moles in our sealed container, same R. What if we say, let's hold pressure constant, right? Let's keep that pressure consistent and change the volume and temperature. Now what's going to happen? Well, let's rearrange this a little bit. We'll bring P and nR over to one side. That's going to equal K, right? Times V equals T. All right, so we can kind of move that up around a little bit more and say, okay, V equals T times the constant, right? So now graphically, right, we've got volume here, temperature here, y and x, but look at that. If temperature goes up, what's happening to volume? It's also going up, right? And it's going up linearly. There's no exponent or anything like that. Boom, nice linear graph. So this is Charles' law. Charles' law says when we hold pressure constant, which is isobaric, it's called isobaric. We're holding iso, stillness, right? Baric, pressure, like bar. So isobaric, we're holding pressure and we have our moles and our gas constant as constants. That means we have a direct linear relationship between volume and temperature because they are on opposite sides of the equal sign, right? So in order to keep equilibrium, if you increase one, you have to increase the other. So this is a nice direct relationship. This will always be true with two variables that are on other sides of the equal signs. So following that pattern, let's do our last one, which is now our final variable that we're going to hold constant. Again, all these laws, we hold the moles constant. So our Gay-Lussac's law is going to hold volume constant. If you guessed that, you are absolutely true. So volume is constant. That is called isovolumetric. Isovolumetric, again, let's see, these guys are constant. This guy's constant, so it'll be nR over V. But now we have temperature and pressure, again, on opposite sides of the equilibrium, right? So just like Charles's law, we'll have pressure here, temperature here, nice linear relationship. So that's going to be our Gay-Lussac's law, again, in an isovolumetric setting where we have constant gas moles. Our pressure and our temperature will be a direct linear relationship, positive and direct. Now, all of these can also be ratios for different containers of gases or different sides of containers. So just note that when we have our pressure and temperature on opposite sides, if we're comparing two of them, we would do pressure over temperature 1 over 1, pressure to temperature 2. All right, this is going to be true for Gay-Lussac's law. This is also true for Charles's law, where we'll have volume 1 over temperature 1 equals volume 2 over temperature 2. This is when we have two sides of like a closed system or container and we're comparing, right? And then for our, that's again Charles. And then for our Boyle's law, this is the one that's different, right? So for our Boyle's law, we have them on the same side. So pressure 1, volume 1 equals pressure 2, volume 2. So now we can see here, right? Okay, if we're increasing the pressure on this side, we'll have to decrease it on that side for volume. So again, these are all equilibrium equations, but see how they're all derived from the ideal gas law? So you really only need the ideal gas law to understand what's going on here and to figure out where I need to hold things constant. So personally for me, it's good to know these names and to know that Gay-Lussac is pressure temperature, Charles is volume temperature, and Boyle's is pressure volume. But really mathematically, I'll usually just base it off of the ideal gas law and hold whatever needs to be held constant as a constant. So I hope that helps you there. Let's go ahead and answer our question. So this question also has a little math too, right? A little unit conversions, which never hurts. So I'm going to again show you how I would do this on my test day. You don't have to do it exactly as I do, but it is a good strategy to develop a consistent pattern when answering math questions. So let's go ahead and start here. What is the estimated volume of 2 grams of an ideal gas? So I always start, before I even try to answer the question, I'm writing down every number they give me. So 2 grams of the ideal gas, and that molar mass is 8 grams per mole. I just have those ready to go because I know I'm probably going to need to get to moles. At a temperature of 300 Kelvin. So my temperature is 300 Kelvin. Okay, good, check that. Kelvin's a good number. At 3 atmospheres for pressure. Again, that's a good number because we're going to use R, 0.08. I'm just going to use 0.08 here. Liters times atmospheres over moles Kelvin. All right, so the thing I'm going to need to convert here is going to be moles because I only have grams. I'm going to go ahead and do that first just so I don't forget. So whenever I'm going from grams to moles, I divide, right, by the molar mass. So 8 grams per mole, grams cancel. 2 over 8 is going to be 1/4 or 0.25. You can write it out however is more comfortable for you. So that's going to be our moles. And again, when we're going from grams to moles, we divide. Moles to grams, multiply. It's a good thing to get very comfortable doing. And then what I'm going to do, my step 1, writing everything out. Step 2 is I'm going to simplify these answer choices here so I don't accidentally pick the wrong one just because my units were weird. So for me personally, I like to put everything in base unit scientific notation. So 2 liters is just going to stay as 2 liters. But B, 0.02 liters is going to be 2 times 10 to the negative 2 liters. Again, because I'm going to do my math in scientific notation, it'll be easy to compare when I get there. Then we have 0.2 milliliters. Well, 0.2 is 10 to the negative 1. Milliliters is 10 to the negative 3. So this is 2 times 10 to the negative 4 liters. 20 is 2 times 10 to the 1. Milliliters is 10 to the negative 3. 10 to the 1 times 10 to the negative 3 is 10 to the negative 2. All right, so now I have all of these out. So it's 10 to the negative 2, 10 to the negative 4, 10 to the negative 2. Wait a second. These guys are saying the exact same answer. That can't be the case. So we can eliminate B and D right off the bat because they're exactly the same. Doesn't always happen on the MCAT, but once in a while, it's really satisfying to eliminate an answer just because you can't have 2 correct answers. So just so you know, that's a really good habit to get into. Now let's go ahead and set up our equation. So we do have PV equals nRT, but I gotta tell you, you could just use our units here, right? We know that we need to end up with liters. So we're gonna put our 0.08 on the numerator. I'm gonna switch that to 8 times 10 to the negative 2. All right, and that's liters times atmospheres over moles Kelvin, right? So let's just do units. Let's pretend we don't know the equation. Well, we gotta get rid of atmospheres, which means we need to divide by pressure, right? That will allow us to eliminate atmospheres. And then we need to multiply by moles to get rid of the moles, which I'm gonna do as 1/4 moles. I'll show you why I did that in a second, but that's gonna cancel out my moles. And then I need to also multiply by kelvins to cancel out my kelvins, right? So now I know I'm gonna be multiplying by 3 times 10 to the 2 Kelvin. Again, I put everything in scientific notation. It's a lot easier for me to look at those individual mantissas and see what I have going on. So now I have my setup. Even if I didn't know the equation, I could use my units to figure out where I'm going. Amazing. So now we have 1/4 times 8 times 3 divided by 3. So what can we do right away? For me, I'm just gonna try to clean this up. This is gonna be divided by 3, right? So that leaves me with 1 times 10 to the 2. And then 1/4 times 8, well, that's really 8 divided by 4, right? So that will simplify me down to 2 times 10 to the negative 2. And that's gonna be 2 times 1, which I already know I'm gonna get because all of my numbers are in 2. So I'm confirming that I'm doing my math correctly. So now I just need to double check my exponents. 10 to the negative 2 times 10 to the 2. We add exponents when we're multiplying exponents. Negative 2 plus 2 is 10 to the 0. So what do I have here? 2 times 10 to the 0, which is perfect for my answer choice here, 2. And there we have it. We have now done PV equals nRT, but I will tell you, 90% of the time, all the units will be right there for you. So I don't want you to panic about which gas law to use and all this stuff. Just use your units and solve from there. Now for my hot shots, did some of you pick up on like, hey, I had moles, I was looking for volume. Couldn't I have just used the molar volume of the gas? If you don't know what I'm talking about, let's talk about it next because this is super important. So the molar volume of any ideal gas is 22.4 liters per mole. So this is essentially saying that 22.4 liters per 1 mole of an ideal gas. That's wild, right? That's huge. Now an ideal gas is defined by a couple of parameters. Number 1, they're super small. In other words, they have incredibly low within molecular volume, which means just basically that the molecule itself can't be big enough to have its own volume that matters. If it does, it'll throw out our calculation because we don't take the intramolecular volume into account in the ideal gas law. Second, they need to have no intermolecular forces. Intermolecular, meaning between molecules. So we're talking hydrogen bonds, dipole-dipole interactions, London dispersion forces, right? All that. No intermolecular forces, they have to be purely nonpolar. And you may be thinking, but Amanda, all molecules have some level of intermolecular forces. This is true. This is why it's an ideal gas law and not a real gas law. But there are some gases that come really close, like helium or hydrogen gas. But they're very small and they tend to be very nonpolar and have very, very few intermolecular forces. These no intermolecular forces allow for what's called elastic collisions. So that's just kind of under this category, which just says that if they do run into each other, they're going to just bounce back off, equal and opposite, Newton's law kind of deal, and they're not going to interact or like be attracted to each other in any way. Because again, if they're attracted to each other, if they stick together more than we expect, our volume measurements will be off. So all of this is to make sure that our volume measurements are accurate, which is why it has to be an ideal gas law in order to use this volume per mole. But the second rule with this, and this is super important, it needs to be at, I'll write it in big letters, STP. All right, so you're only allowed to use this number if you're at STP. What is that? Standard temperature, which is 0 degrees Celsius or 273 Kelvin. and 1 atmosphere, right, of pressure. So if we think back to our question here, we were at 3 atmospheres and 300 Kelvin. We were not at STP, so we can't just use our molar volume of our gas. We have to go through the whole ideal gas law. Again, we're still in the ideal gas law conditions, but we're not at STP. If we were at STP, I give you full permission to use 22.4 liters per mole and then just multiply by the moles to get our numbers here. But we weren't there, so we had to use our full ideal gas law. All right, that's my final stipulation. I hope this video was helpful for you. Please feel free to ask any questions in the comments below. And as always, happy studying.